We're now going to develop a measure of how tightly clustered a scatter diagram is about a straight line. If you just look at a scatter diagram, it's actually quite hard to say numerically how tightly clustered it is, even if we have some understanding of what that means, because our eye is very much affected by the choice of scale. But if you have a set of scatter diagrams all drawn to the same scale, as I've drawn these, then it is clear when one of them is more tightly clustered than another. This third one, for example, appears to be much more tightly clustered about the x equals y line than, for example, this one. The first one is rather loose, the data are fuzzy, the middle one somewhat less fuzzy, and by the time you're looking at the third one, the clustering is quite tight. Notice that the horizontal scale is the same, -2 to 2 for all of them. Vertical scale is -3 to 3 for all of them. Yes, I've drawn data in standard units. So what we're going to do is to try and produce a measure that says how tightly clustered each one is, and we're going to get one for which the value for this third diagram is higher than the value for the first. All three are going to be positive because you can see the positive trend for all of them. And that measure is called the correlation coefficient. And because that is such a mouthful, it is affectionately abbreviated to R. And it turns out, by the way it is calculated, that it is always a number between -1 and +1. And it measures linear association, that is, how close the scatter diagram is to a straight line. Now, before we discuss how it behaves, let's run through how you calculate it, and then we will discuss its properties, and in subsequent sections we will study how to use it. So we'll start with a simple data set, as we've always done when we've done our first calculation of any measure. And so I have 5 points, and the scatter diagram looks like this. The first point is 1, 2, so that's 1, 2, that's this one. The second point is 2, 3, the third one is 3, 1, 4, 6, and 5, 6. So if I look at that scatter diagram, certainly it is sloping upwards, so I expect the correlation that I calculate to be positive, and I do not expect it to be +1. +1 is the maximum it can be, and there's a natural sense that that should be the perfect straight line. So I'm expecting R to be positive, but not +1. Well, fine. So what is it? Here are the moves. In order to calculate R, we notice that we could tell a great deal about the shape, whether it's linear or not, without looking at all at exactly what numbers were on the horizontal or vertical axes. So step 1, convert everything to standard units. So let's take a look at this. My points were 1, 2, 2, 3, 3, 1, 4, 6, and 5, 6. I've decided to call the first coordinate x and the second one y. You are welcome to do it the other way around. I will first convert x and y both to standard units because I'm just interested in shape. I'm not interested in exact numbers on the axes. So how do I convert to standard units? Well, I know how. I have to calculate the mean of x, the SD of x, and then to convert the 1 to standard units, I must do 1 minus the mean, which is 3, that whole thing divided by the SD, which is 1.41. And I end up getting minus 1.41. If I do 2 minus 3 divided by 1.41, I get minus 0.71, and so on. And so also I convert y to standard units. And just so we haven't forgotten standard units, the 0 here means that this value of x was at the average. Was that actually true? This value of x was 3, and the mean is 3. Yes, indeed, that was correct. Negative signs mean that the value was below average. So for example, this one, the minus 1.26 for y's, the y was 1, the mean of y is 3.6, so yes, that value is below average. So it's the same old standard units that you know how to compute. And now what we're going to do is the move to compute R, which is we're going to multiply pairs of standard units. So you take minus 1.41, multiply by minus 0.78, you will get 1.1 roughly. Minus 0.71 times minus 0.29, and you've got 0.21. And so on. And so you have a set of products, bear with me for a moment, you have a set of products, do the simplest thing to them, take their mean. That is going to be a number between minus 1 and plus 1, trust me. That is R. And it is positive, as we had said it would be, and it is not 1. That is also what we had said it would be. Positive, but not 1. Now, as to why this produces something that measures linearity, that is much too hard to explain in algebraic detail at this level. One of the things you ought to be able to see, though, is that it will in general give you the right sign. So let's take a look at these two pairs of standard units. That's when x was 5 and y was 6. Both of these values were above average. Well, if both are above average, then both standard units will be positive. And so when you multiply them, you'll get a positive product. Here, both the x and the y were below average. And so when we multiply the two negative standard units, we again get a positive. Now, what does positive association say? Positive association says above average values of one go in general with above average values of the other, which is the same as saying below average values of one tend to go in general with below average values of the other. If that's the case, the multiplication will give minus times minus equals plus, plus times plus equals plus, and in the end you will have the right sign. For negative association, if you had pluses in one of the standard units, typically you would have a minus with the other, and then when you multiply you will get overall a negative sign. So at least you can see that the multiplication is the right thing to do as far as the sign is concerned. Once you've done the multiplication, the average is by definition the correlation coefficient. So not hard to calculate, laborious. You have to convert x to standard units, you have to convert y to standard units. After that it's easy. Now this method of calculation, which we will summarize in a formula, as always we write our formula in two languages. Here's the formula in English. Convert both lists to standard units, multiply the corresponding pairs of standard units, and then take the average of the products, and you're done. For those of you who like math language, here's the formula in math language. So you have two lists of numbers, x, y, and I have n such pairs. Convert the generic x to standard units, convert the generic y to standard units, multiply, and then take the average. And you have R. I'm using the same notation here as we've used in our algebra supplement. Those of you who haven't read it or aren't interested in it, why don't we just move on? Because you can compute exactly the same thing using the formula written in English. Now the way of calculation immediately tells us that R has certain properties. First, the calculation only uses standard units. So R is a pure number. It has no units, no Fahrenheit, no centigrade, no inches. It's a number. It is between -1 and +1, and trust me is all the reason I'm going to give you. Those of you who have done some more advanced mathematics, this is a consequence of the Cauchy-Schwarz inequality, which I am not about to prove. Let's say what we've said about the extreme cases. When R is +1, you have a scatter diagram that is a perfect straight line sloping up. When R is -1, you have a scatter diagram that is a perfect straight line sloping down. What happens when you switch the variables? Why do you care about switching the variables? Well, you want to know, if somebody tells me the correlation between height and weight, then what can I say about the correlation between weight and height? Well, in fact, it's exactly the same. The degree of clustering about the straight line stays exactly the same, regardless of which one you've put on which axis. And just to make that point algebraically, how did we calculate the correlation? We converted the two variables to standard units, and then we multiplied. Now when you multiply, it doesn't matter which one you call x and which one you call y, you're going to get the same product. So algebraically, the products of standard units are going to be the same regardless of which one is on which axis. And so r is going to be the same. Some people find this a perfectly acceptable and convincing argument. Those are the people who love algebra. For others, this needs to be explained in a picture. So why don't we take a look at a picture? Because there should be no doubts at this stage. Here is a scatter diagram of midterm and final scores in a lower division statistics class in Berkeley. And so the midterm was scored out of 20, the final was scored out of 40. You see these vertical stripes. That's because on my scale, that's 10, all the people who got 10 on the midterm, all the people who got 9 on the midterm, and so on. So the scores were discrete. And you can see that this correlation surely would have been positive. The scatter diagram is sloping up. Now, the choice here was to draw midterm on the horizontal axis and final on the vertical. If we had made the opposite choice, the picture would have looked like this: final on the horizontal axis and midterm on the vertical. And what has happened? We have taken our original scatter diagram and we have flipped it about the x equals y line. And so you can see these 3 points, these are the 3 people who didn't take the midterm. These 3 points here, which were on a vertical strip, are now on the corresponding horizontal strip down here. And the point regarding correlation is that this figure has a certain degree of clustering about a straight line, and this figure has exactly the same degree of clustering about a straight line. We haven't affected the degree of clustering at all. So r remains the same. And what does this do for us? What this does is it says you can talk about the correlation between midterm and final, or the correlation between final and midterm. You don't have to stress about which variable you are uttering first. Moving on to some other similar observations. Changing units, you've seen, is going to be quite important, standard units in particular. So what happens when you add a constant to either x or y, or possibly both? Well, when you add a constant to x, if you add 10 to all the midterm scores, the scatter diagram just slides 10 units to the right. If you add minus 10, then it will slide 10 units to the left. So adding a constant just slides the scatter diagram about. It does not change the degree of clustering about a straight line, so r stays exactly the same. And those of you who like algebra, if you add a constant to one or indeed both of the lists, you will not change standard units. And since r is based on standard units, it does not change. Similarly also, if you multiply one of the lists by a positive constant, and indeed you can multiply the other one by a different positive constant if you wish, you will not change standard units and r will stay exactly the same. Why does this matter? Well, we've just said if you're looking at the correlation between height and weight, you might just as well say the correlation between weight and height. It'll be the same. What this property is now saying is that you don't care whether height was measured in inches or centimeters. Because the transformation from inches to centimeters is take the list in inches and multiply by 2.54. That multiplication does nothing to standard units, and so it does nothing to r. And so you can talk about the correlation between heights and weights, and you don't have to worry about the units in which they were measured, and you don't have to worry about which is on which axis. Now I'll end this discussion with something that's a little bit technical, and that is what happens when you multiply by a negative number. And what happens when you multiply a list by a negative number is that entries that were big before have now become correspondingly small. And so the standard units don't change in their value, but they change in sign. Something that was 2 standard deviations above average will now be 2 standard deviations below average. So what will happen to r? Well, the numerical values of the products will all be the same, but their signs will be flipped. and so R will have the same absolute value, but its sign will be switched. So if you have a pair of variables and the correlation is 0.7, and you multiply one of the variables by minus 143.2, then the correlation between your new pair of variables is negative 0.7. And so I know some of you are thinking, what if I multiplied both of them? What if I multiplied one by minus 143 point whatever and the other one by minus 18? Well, that first multiplication would switch my 0.7 correlation to a minus 0.7 correlation, and the second multiplication would switch the minus 0.7 correlation to a plus 0.7 correlation. Multiplication by a negative constant is not very common unless you are looking at some, for example, your right answers and wrong answers in one of your previous exercises. The number of wrong answers was 10 minus the number right, and there was a multiplication by minus 1 there. That's a situation in which this might come into play. But much more common is multiplication by positive constants. That's what happens consistently when you are changing units of measurement. So to summarize, R measures the degree of linear association. It is positive when the scatter diagram slopes up. It is negative when the scatter diagram slopes down. It is a pure number. It does not depend on the units in which you have measured your data. It does not depend on which you have chosen to put on which axis. Now, R is a quantity that's used a lot, and we will spend the next segment looking at it a little bit carefully to make sure that we use it appropriately. And then in the next section of the course, section 7, we will use it in calculations to estimate the value of one variable based on another.